Hello, welcome to this section 2B. The focus of this section is going to be on process control block PCB, then different process state models. We will start with 3 state models, then in the next section we will continue with the 5 state, 6 state models. Okay, what is a process control block? Now, as I have mentioned earlier, the most important job of a OS is to manage different processes. Now, in a system, there is going to be many processes running. Now, unless OS maintains the information about each of the processes running in the system, it will not be able to manage them. So they need to have a record of what all the processes are active in the system and what are their current states, where are they physically, and who are the owners of this process, and what is it currently doing, or whether it has asked for something, whether it is waiting for some event. So it should know everything about all the active processes in the system. For that to happen, similar to what we have an Aadhaar card where every individual in India is tracked with all our activities, whether we are filing tax, what are the transactions we are doing with the bank, and what is the PAN number linked to your Aadhaar card, and what are the accounts you have connected to your Aadhaar card. So everything about an individual in the country is being tracked with one single information having an Aadhaar card. Similar to that, OS maintains one record of each process in the system, which is called process control block. So this is going to be opened, like every individual born in India is given an Aadhaar card. When a new process is created, a PCB is allotted. It is maintained till the process terminates or exits the system. So this PCB, process control block, maintains all the information about the process. So let us see what happens inside. What is inside? Now, before I go into the PCB, let me just briefly tell you about how is it maintained. There are different ways they are maintained. As I mentioned that in the main memory, OS is there, residing already. That means what? The resident set of the OS is also there in the memory. You know that OS is a software, so it also has its own code, its own data, and its own stack, kernel stack. And maybe it may not use heap, or could use that also, because this this particular memory what the OS is holding will also be having different segments, code, data, and stack segments. But only difference is this is going to be a kernel mode and it's going to be critically well protected against any other user process accessing it. Now, if it has to maintain the PCB, process control block of all the processes, one option is to have the PCB within the OS data structure. In that case, it is protected. Sometimes some OSs like Linux might maintain it in the along with the stack of kernel stack. Okay, so let us not go into the details of how different OSs maintain it. Or in terms of real-time operating system, it could be an array of PCB entries. Okay, array of structure, which is a PCB structure starting with 0 to maybe 100 now, or 99. Now, how do you decide how many entries you need to have in a OS? It depends on how many processes are going to be active while the system is running. So in a real-time operating system, the memory is limited, so the number of entries reserved for PCB also limited, and number of tasks that you can create in a real-time operating system also limited. So the PCB number of entries for PCB will be restricted. So if you try to create more than what is allocated PCB entries, then it will say that you cannot create any more processes, new processes. Whereas in the kernel like Windows or Linux, where it is for the desktop applications or a big server application, the number of processes that it can create will be unlimited. Or there may be some physical limitation, but more or less it is not restricted as if in a state of in a place where RTOS is having a restricted memory, so it will have a limited number of process control block allocated within the OS. So this I am giving you as an additional information for you to know how the PCB is maintained by the OS. Now let us go into the details of the PCB. Now, as I mentioned that PCB itself is a structure because most of the OS is implemented in C. So this is going to be a structure. So these are the elements of a structure PCB. Now you need to have an identifier, unique identifier. It could be an index into the PCB array, or it could be allocated and stored with as a part of the entry. And every process has a state. We saw, we are going to see different states, new, ready, running. There are different states of processes which is going to be seen in this lecture. And then there could be a priority within system. There can be very high priority processes and low priority processes. And of course it needs to have a program counter where the current instruction is being fetched from there. So that's a current instruction the process is planning to execute if it is given a chance on the CPU. Then there are different pointers. It could be pointing to stack, or it could be a pointing to some data memory. And then context data, which is set of registers R0, R1, R2. Every register within the CPU, that information, the content of that information is stored. Once the process starts executing, it will have its own state. And then IO status. Suppose if it has initiated some interaction with the hard disk, or maybe with the network, or with the serial port. So it could have opened some different files. So that information is captured in the IO information. What is accounting information, which I already shown you or explained. What is the amount of time it has spent on CPU, how much of memory it is using, okay, how much of hard disk maybe it may be owning it. It could be anything. I know who is the owner of this process and what are the groups. Well, it could be accounting information, could be many. When this process was created, how long it has been running, how long it has been block state. It could be anything. Okay, any information about the process or accounting information about the process. So PCB is a data structure created and managed by the OS for every process in the system. The significant point about PCB is that it contains sufficient information so that it is possible to interrupt a running process and later resume its execution. Interrupt means stop it. That means pause. It is running on the CPU. I decide to take out the process from the CPU, and then I can bring it back into the CPU and start running it. So I should be able to do it. In that case, the context information should be preserved as a part of the PCB. And when it continues, it should look like as if nothing has happened. The process itself will not know that it went out of the CPU and came back, except that it has lost some time in the bargain. So if it is keeping track of the time when it sort of created, when it was created, and what is the current time, then it will see that it has not made much of progress. It has been sleeping for a while, or it has been blocked, or the CPU has decided not to schedule it at all. So there could be many reasons for a process to be slow, or process is not being run on the CPU. Now, process control block is a key data structure that enables the OS to support multiple processes. As I told you, if it has to maintain multiple processes and make sure that all of them are given equal chance or fair amount of CPU, and then keep track of what is the state of the process and what is it currently doing, where it is residing, whether it is in the main memory or it has been swapped out to hard disk, all that has to be captured in the PCB. Now, when a process is interrupted, that means it could be possible that OS decided to block it, or process itself said that I want to sleep for a while, or process itself said that I want an IO to be done, I want to read some file, or I am waiting for some data from the user, or it could be anything. So the program counter and the process registers are saved in the appropriate fields of the PCB so that it can be run later on. Okay, it can be restored or it can be brought into the CPU and start running it on the CPU. So this is a process area in which this status is stored. The PCB could be in the process area, or it should be protected. Remember that it's a part of the OS data structure and it should be accessed only in the kernel mode. That's what I'm trying to tell you about this. Now let us go into the details of the entries. Identifier is a unique identifier associated with the process. So no two processes will have the same identifier. Similar to each one of us have a unique Aadhaar card in India. State. If the process is currently executing, it will be in running state. Otherwise, it could be on different states, which we are going to see now. Priority. If you are going to be associating a priority, some numbers can be given. Different processes, different OSs have priorities kind of 0 to maybe 255. In that case, a OS can decide that a lower number is a high priority or a higher number is a high priority. It is completely implementation dependent. There is no standard way of or standard um, in deciding the priority number. Whether a lower number is high priority or a higher number is higher priority is completely implementation dependent. Program counter, of course, you know that this is the register in the CPU which is pointing at the address where the next code or instruction to be fetched from. Okay, I hope you get it. The assembly instruction which is to be fetched from the memory, code memory or a text memory that needs to be executed by the CPU. Memory pointers, it could be any pointer or any register which can be holding a pointer, or R13 itself is a pointer because it is pointing at the stack address. So that needs to be saved. Context data, any register content or flags, last arithmetic operation what it has done, it would have affected the flags like negative or zero flag or carry flag or overflow flag. That has to be preserved so that when it comes back, and then if you are taking action on the flag branch equal to or some instruction you are going to execute, it should reflect the last operation done by the instruction while the process was running. So even the flag content should be preserved as a part of the context. IO status, I told you that anything to do with the file, accounting information about any files open or how much of processor time it has consumed, many. Now, I mentioned something about process states. So let us see what are the process states. Here in this lecture, we are going to see only two-state model and a three-state model. Okay, later on in the next lecture, we will see more number of states. Now, what do I mean by state? A process when it is like individually, each one of us go through different states. Like in the childhood, we are adult. We come from an infant, and then the child, then adult, then we become maybe old man or if you cross 100 it could be different state. So these are the different states of a human being. Similarly, processes also go through different states. Okay, it's not that one way around, it can go through different states and come back. Like you may decide to be in the school as a student, then you go to a job, you are an employee, then you can come back to a college and do a PhD, then you become a student again. Similar to that, the process also can be in a running state or a block state, or it can be any different number of states it could be throughout the life of the process. So it enters the system. That means when you are creating a process or when you are running a program, it is entering a state called not running. So initially when the process is created, it's not put on the CPU yet. Then it is in the not running state. And when the scheduler, whatever the part of the OS module, decides to pick this process and make to run on the CPU, then the state is made as a running. And then if the process decides to exit, it goes out of the system, or scheduler decides to pause the process. That means it doesn't want it to run forever. It wants to take it out of the CPU. Then it goes into not running state. So in this simple scenario, we are assuming that there are only two states, not running and running. There is no other states defined. Now dispatch means a process is picked up from the not running state to a running state. That means it is made to run on the CPU. Pause means a process is picked up, forcibly taken out of the CPU and put it in the not running state. Why are we doing this? Because the scheduler is there to make sure that the CPU is shared between different processes. Otherwise, only one process can hog the CPU and nothing else can happen in the system. So it has to be forcibly taken out if the process is running forever. So pause means we are saying that okay, you have run enough on the CPU. Now you are going to freeze. I'm going to run. I'm going to freeze you. That means whatever may be the state of the currently running process is going to be preserved in the PCB, which is process control block, and then other process is going to be brought into the CPU. So we can construct the simplest possible model by observing that at any time a process is either being executed or by a processor or not. In this model, a process may be in one of these two states, running state or not running state. This is the most simplistic process state. but not useful because it does not capture the real life states. Okay, you cannot say that a human being is a child and then a old man. Okay, there's nothing in between. It's not possible for a process or a human being to move from a child state to uh, a old man state. Okay, you have to go through different states. Okay, so processes also go through different states. So this is a simplistic model. Now remember, we had a field as a state in the PCB. Okay, that is also linked to it. Okay, now, how will the state might have been implemented in an OS? It could be enum. Okay, enumerators. You can define enum type like new, running or not running. No, lot of states. Okay. Now, what is the role of dispatcher, which I mentioned here? That the dispatch is happening to pick a process from not running to running state. Now, remember, in a system, it's not that only one process is going to be running. Though state transition is for a single process, okay, state transition is for a single process. It could be moving between different states. Similarly, different processes could be moving in different states. Remember, each one of us in the world, maybe a child or different age groups are there. They may be living in their own life. They are transitioning from one state to the other state. But there are many human beings in the world going through different states. Similar to that, in a system, there are many processes and they will be migrating from one state to the other state. So the state transition, what you see is a possible movement of different states. But each process may have their own movement in this state. Okay, state transition. So state transition is a template where you are saying that these are the possible states and these are the possible transitions. But these are the possible transitions that some transitions are not allowed. You cannot say that the process without moving into a new state, it is exit. No, if it is not born, you cannot say that somebody has died. So similar to that, a process cannot exist. You cannot say that without being created, it is exited from the system. Okay. So similar to that, the template is created and possible transitions are explained, and the process can go through different state, and those transitions are specific to a particular individual process. So in that case, there are many processes in the system. That means we need to have some way of maintaining them or managing them, and which is required for the OS to make sure that every process in the system is managed properly. So it maintains a queue. That means the queue may have the PIDs of each process. It's not that it's going to have the PCB itself here in the queue, because PCB is in the memory and you have an ID which is referring to a particular PCB entry. So if you are maintaining an ID here, that is enough. So you will be able to go back to the PCB structure and get to know about what all is there in it. Okay, so that's how it is maintained. So there is a queue. That means there are many processes in this queue, and then a dispatcher is picking up the one in the head of the queue and then puts it in the CPU. So when the OS creates a new process, it creates a PCB entry and then puts it in a not running state and adds to the queue at the end. Now the process exists. It is known as now the process exists. It is known to the OS. Okay, and it is waiting for an opportunity to execute on the CPU. I hope this is clear to you. This particular bullet. Then from time to time, the currently running process will be interrupted based on the time. Okay, some quantum, that means 10 millisecond, 5 millisecond, it will be allowing it to run, and then a process will remain in the running state for some time, and then it is forcibly taken out and added to the end of the queue, because we want to have a fair share of the CPU for all the processes in the queue, whichever is in the not running state, where you have to give equal. No, there is no priority here, so we have to give equal opportunity for all the processes in the system. So there is some OS when it is brought up, when it is built with some configuration, and it need not be built with the configuration. It can be configured while booting the OS also based on some configuration files, where you can say that I want quantum time of 5 millisecond or 10 millisecond. Then the OS will be booted with that value and it will maintain that much of quantum time for each process. So the former process moves from the running state to the not running state, whatever was running on the CPU, and then something in the head of the queue is moving into a running state. Okay, so this is a very simple. What is stored in the queue of the dispatcher? I already told you, it's a pointers to the PCB structure, or it could be an ID, process ID, which is an index into the array of structures. Okay, I hope this is clear to you. You always think about how it could be implemented in OS. because all of us are programmers, and when we are studying OS, we have to link it with the implementation of the OS, because OS itself is a program mostly written in C. Is this queue FIFO or LIFO? First in first out or last in first out? It looks like FIFO, because first in into the end of the queue will come out of the queue. Okay, so it's FIFO. Now dispatcher queue. Let me explain a little more. The queue is a first in first out, and the processor operates in a round robin fashion on the available processes. Okay, whatever is there in the queue. Each process in the queue is given a certain amount of quantum, one by one in turn, and then to execute and then return to the ready or dispatch queue unless blocked. Okay, this I am saying, this one with this these are all different names of it, so I will call this as a dispatcher queue. Okay, and then we are not assuming that it is blocked also. Okay, blocked will come to that later on. It is only the process. These processes are never getting blocked, and they just keep running, and then they are forcibly taken out, and then they go to not running state. So, however, even with the simple example that we have described, this implementation is inadequate, because some processes in the not running state are ready to execute while others are blocked. So, there can be possibility that some processor would have asked for an IO. In that case, it should be captured as a blocked state, because what I mean by blocked means, suppose a process saying I want to open a file. Now you have written a code fopen, and then you are given a file name and then the directory wherever the path is, whatever, or the path could be given as along with the file name also. And then I am opening it for read purpose or append purpose or read and write purpose or whatever. Now until this fopen is executed and completed, and then it returns some FD file descriptor, this program cannot go further, because it is supposed to get the file descriptor and operate on the file, but the file is in the hard disk and it has to be read by the OS, not only by OS but by the device driver of the hard disk, or maybe a solid pen drive. So it takes a lot of time. In that case, it will be in a blocked state. We had to bring in another state which is different from not running state, because it is not running not because CPU is not available. It is not running because it wanted to do something and which is yet to happen. It is waiting for some event, which is a reading from a file. So we found out that this two-state model is inadequate. So using a single queue for all this not running as well as block state will be a confusion, because every time when you are looking into the queue, you have to check whether this is in which state, whether it is blocked for some event, then you have to skip and then go to another thing. So it's a painful implementation. So let us find some better implementation of this. So rather, dispatcher would have to scan through the list to look for a probable right candidate to be allocated on the CPU. So what are the design elements related to the processes? From this simple model, we can already begin to appreciate some of the design elements of the OS. Each process must be represented in some way so that the OS can keep track of it. We have found a way it is done, PCB, okay, process control block. That is, there must be some information related to each process maintained in the PCB, and there should be a state associated with the process, because we understood that that is required. Processes that are not running must be kept in some part of the queue, some sort of the queue, waiting their turn to execute. Some which are blocked needs to be in some other queue. And then structure of the OS dispatcher suggests that there is a queue in which each entry is a pointer to the process control block. You know that it could be a pointer to the control block, or it could be an index which can be accessed as an element of an array, right? Both are pointers only. Alternately, you can also have a linked list. Okay, there's possibility that you can put it in a linked list. Need not be an array of element. You can maintain a linked list, which is little time consuming in terms of tracking, running through it. So index based, array based implementation is faster. Okay, fine. Now we just thought about different ways OS could implement it. Okay, now let us see that we bring another state called blocked state. I told you that blocked state means it is waiting for some event to happen. Maybe waiting for a keyboard entry, or waiting for some data to come on a port, or it could be that it wants to open a file. It could be anything. So a state diagram of a process captures the life cycle. Okay, it's a life cycle. Now newly created process gets into ready state. Remember, a ready state is a one where the process has everything available to it for running except the CPU. Okay, that is very important sentence to be remembered. Ready process, a process in a ready state, processes in the ready state are the ones which has everything available for it to be running on the CPU except the CPU. Now, when they are given CPU, they are ready to run. When I say it has everything, that means it suppose if it the resident set is available in the main memory. If it wanted some file, it is also open and available on the main memory. Then only it can go further and start running on the CPU. Now, let us look at all the transitions before we get into the next one. So it is picked up for running and then forcibly process can be removed from the running state because the time quota was over. Okay, it has run for a while. Now it's time for another process to be given the CPU. So it will be brought back to the ready state because it is not waiting for anything. It's wait, it was forcibly taken out by the OS, so based on the timeout, so it is brought here. Whereas if the process asks for some IO or event or some keyboard entry, some user has to feed in some information, then it is going to wait for some event. In that case, there is no point in keeping it on the CPU because it's not going to progress further because it is in the waiting stage. Or it wants to sleep for a minute or 1 hour. In that case, no, 1 minute also is a longer duration from the CPU perspective. Okay, it's all running in gigahertz clock. Then you can imagine that it's running at nanoseconds. So it needs to be blocked. It should be moved out of the running state and it should be in a blocked state. And then when it becomes ready, when that unblocking, when the condition for which it was waiting has happened. That means file opened. Yeah, the file has been brought into the main memory. It is open. Or if it waiting for 1 minute, that 1 minute time is over. Now it is ready to run. So our keyboard entry, the user has entered something, so I need to process it. So anything when the process comes out of the block state, it doesn't move back to the running state directly. Always it comes to the ready state and then it is picked up by the dispatcher or the scheduler, which picks the right process from the ready queue to running state. So running state is not decided immediately just because a process has come out of the blocking condition. Many processes could be getting out of the block condition, but one of the ready processes need to be picked up. There may be somebody waiting in the ready queue already. So you cannot say that some process has come out of the blocking state, so I will make it run immediately. It should be fairness, it should be maintained. So the state represents the execution states of the processes and how they transition through the different states of processes. Each active process has its own execution state. That's what I'm saying. Each process has its own state. This transition is a template. A process may move into this and they may be residing in one of the states based on where they are in their execution state. Each process go through the life cycle, sequence of transitions, which may or may not depend on the life cycle of other processes. Remember, different processes are going through its own life. Each one of us have our own life state. It's not, maybe there may be some impact of one person's state on somebody else's if they are related or something, but we live our own life and we go through different states of transitions. Similar to that, processes also go through different state transitions and they are mostly, sometimes some are independent, mostly they are independent too. Related processes may be, cooperating processes may be dependent. Unrelated processes, there is no relationship between state transitions happening between unrelated processes. Okay, so three-state process model, and this is the one, and this is the new one we are going. So two-state model has been found to be inadequate, and we added a block state, and then the processes which are blocked for IO as well as the processes which are taken out of the CPU because of exceeding the time quantum are both kept in the same dispatcher queue. Okay, this is what I'm saying. It could be here or it is moved here. Okay. Now this makes the OS to go through this list multiple times to choose the one which is not blocked on IO to run. So just telling you that this two-state model is insufficient and I want a three-state model because it has to go through this queue multiple times to know whether it's a blocked state or a not running state. So we are deciding to go into a three-state model and we are calling it as a ready state. So What is a ready state? A process in the ready state has all the resources that it needs for execution except the processor. It is normally held in a ready queue until a processor becomes available. Here the processor is waiting to be assigned to a processor. A process is waiting to be assigned to a processor in a ready queue. Process may come into this state on creation while running. It would have been brought into because of the timeout, or it was in block state and it came unblocking into this. So you know different ways they can enter. There are three entries to the ready queue. Okay, so running state is very simple. It's on the CPU. So a process in the running state has all the resources that it needs, including the CPU. It is currently running on the processor. A process can exit the running state for any of the following reasons. How can a process exit from it? It got terminated by itself. Main is no, you exit from the main. That's it. The process is done. So, or you executed a system call for exit, or the process received a control C signal. The user on the terminal decided to terminate the process. I'll give you a control C, then the actively running process on the terminal will be blocked, or sorry, will be terminated. So it could be forcibly taken out. It may not be in the running state. So it could be in the running state also, but it could be in any state. It can be terminated by control C. But if it is running, the possibility is that the process itself has decided to run, come out, or the process can go into a blocked state by initiating an IO request. So it is moving out of running state for many reasons. Blocking. Okay. Second reason is it is getting blocked. Third reason is process continues to run, so it has exceeded the time quantum. OS decided to pull it out from the CPU. So it moves into ready queue. So these are the three reasons a running process could be coming out of the running state. It can be terminated, or it can be blocked, or it could timed out and it is going to ready state. Now, what is the block state? You know very well. A process that needs some resource or a file or an event or an input is in a block state. It usually placed in a blocked queue. There is a different queue for it. The needed resource could be a file or from HDD or a data received on a serial port or a mouse click or a user input. A process can stay in a block tree until that event happens. You cannot limit. Okay, there is no time limit on it. I can wait forever as long as the system is running and its power is there. It can go on until somebody decides to remove it from the system. Okay, the IT administrator may decide that the process has been blocked for our years. They can decide to kill it. So these are the things what has been covered in this section. See you in the next lecture. Bye bye.